Welcome, architects and engineers. We often obsess over flops and parameter counts, but the real war for AI supremacy is being fought in the plumbing. While the world stares at the H100 GPU specs, a massive shift has moved the bottleneck from pure compute to I/O and interconnect latency. As models grow, the time spent waiting for data to travel between nodes now accounts for up to 60% of total training time. This presentation isn't about the neural networks themselves. It's about the ultra-scalable infrastructure, the 800G fabrics, and the memory architectures that prevent these billion-dollar clusters from idling. We are moving from a compute-centric world to a data movement-centric one. Let's look at the hidden tech fueling the next generation of speed. Standard DDR5 simply cannot keep up with the appetite of modern LLMs. Enter HBM3E, or high bandwidth memory. By stacking DRAM vertically and connecting it directly to the GPU via a silicon interposer, we achieve bandwidth exceeding 1.2 terabytes per second. For a senior architect, the memory wall is the primary constraint on throughput. When your model weights are distributed across 10,000 nodes, the ability to fetch parameters from local VRAM determines your token per second floor. HBM3E isn't just a capacity play, it's a 24-high stack architecture designed to minimize the physical distance data must travel, effectively turning the memory into a first-class citizen of the processing unit itself. When scaling to 100,000 GPUs, the network becomes the backplane. Currently, two titans dominate, InfiniBand and Roccev V2. InfiniBand offers a lossless, credit-based flow control that is essentially a proprietary high-speed highway. However, the industry is pushing back with Roccev V2, RDMA over converged Ethernet. This allows us to use standard Ethernet switches while bypassing the CPU kernel for direct memory access. As an infrastructure engineer, your choice here dictates your tail latency. In large-scale training, a single dropped packet can stall a synchronous SGD step across the entire cluster. We're seeing a massive investment in Ultra Ethernet Consortium standards to bring the reliability of InfiniBand to the cost scale of Ethernet. You cannot fit a 1.8 trillion parameter model on one card. Speed is achieved through 3D parallelism. Data parallelism shards the batch, model parallelism shards the layers, and pipeline parallelism creates a production line of execution. The secret tech here is the orchestration layer that manages these microbatches. To avoid bubbles, periods where GPUs are idle waiting for the previous pipeline stage, engineers use interleaved 1F, 1B schedules. Mastering this choreography is how companies like OpenAI achieve near-linear scaling. If your pipeline isn't balanced, you're effectively paying for H100s to sit and wait. We are now seeing the rise of 4D parallelism, adding sequence parallelism to handle massive context windows. Precision is the enemy of speed. While researchers love FP32, production infrastructure runs on FP8 and even INT4. Moving from 16-bit to 8-bit floating point effectively doubles your effective memory bandwidth and compute throughput without changing a single hardware component. But the secret is how we maintain accuracy. Techniques like NF4, normal float 4, and weight-only quantization allow us to compress models by 4x. For a software architect, this means your KV cache, the memory used to store conversation history, suddenly fits 4 times more users on the same hardware. We are seeing hardware-level support for mixed precision casting, allowing the GPU to switch precision on the fly to protect the gradients of critical layers. Inference is often limited by the autoregressive nature of LLMs, one token at a time. Speculative decoding changes the game. We use a tiny, lightning-fast draft model to guess the next 5 to 10 tokens, and then the massive Oracle model verifies them all in a single parallel pass. If the draft is right, we get 5 tokens for the cost of 1 compute cycle. This can increase inference speed by 2x to 3x without any loss in quality. This is purely an architectural optimization. It requires high-speed shared memory between the draft and Oracle models, making it a masterpiece of system design. It's the closest thing to a free lunch in the AI infrastructure world right now. At 700 watts per GPU, air cooling is dead. The next generation of AI data centers is moving to direct-to-chip liquid cooling and immersion tanks. When you have a cluster pulling 50 megawatts, heat is not just a nuisance, it's a structural barrier to clock speeds. Senior engineers are now designing cooling distribution units, or CDUs, that manage the secondary fluid loops. By using liquid, we can pack GPUs closer together, which reduces the length of copper cables and further lowers latency. The secret tech here is the thermal management software that predicts hotspots in the neural network workload and pre-cools specific racks before a training burst begins. In a cluster of 50,000 GPUs, the mean time between failure is measured in hours, not days. If one GPU fails, the entire training job crashes. The secret tech fueling speed is how we recover. Traditional checkpointing to disk is too slow. It can take 30 minutes to save a multi-terabyte model state. Modern infrastructure uses in-memory checkpointing across the high-speed fabric. By sharding the model state in the RAM of neighboring nodes, we can resume training in seconds rather than minutes. This maximizes the effective T-flops of the cluster. If you're not managing state at the fabric level, you're losing 10% of your compute budget just to overhead. NVIDIA is the current king, but the speed of the future lies in domain-specific architectures. Google's TPUs, AWS Trainium, and startups like Grok are redesigning the chip from the ground up for tensor operations. These chips often eliminate the need for complex instruction sets, focusing entirely on SRAM, putting the memory directly on the processing die to eliminate external bus latency. For an infrastructure engineer, this means moving away from general-purpose CUDA to specialized compilers. The secret here is the compiler, the software that maps the neural graph to the physical silicon. Hardware is only as fast as the graph-lowering optimizations that feed it. As we look toward the horizon, we are moving from clusters to AI supercomputers that consume the power of small cities. The secret tech fueling this speed isn't one single invention, but the hyper-integration of memory, fabric, and cooling. For senior software architects, the challenge is no longer just writing code, but understanding the physics of the data center. The companies that win will be those that minimize the distance between a bit of data and a floating point operation. We are building the most complex machines in human history. The question is your infrastructure ready for the scale of tomorrow? Thank you for joining this deep dive into the hidden world of AI speed.